Imagine, if you will, the universe's earliest moments, not as a quiet beginning, but as a maelstrom of unimaginable energy, a cosmic furnace where all the matter and light we now observe were compressed into a state of extreme density and heat. This primordial inferno, often referred to as the Big Bang, wasn't an explosion in space, but rather the rapid, dramatic expansion of space itself, carrying everything within it outwards. From this fiery genesis, our universe burst forth, a crucible of fundamental particles and intense radiation, where temperatures soared to trillions of degrees, making even the concept of atoms impossible. For a brief, scorching period, existence was a brilliant opaque plasma, a superheated fog where light was constantly scattered, unable to travel more than an infinitesimal distance without colliding with another particle. Every point in this nascent cosmos was incandescent, glowing with an intensity that would dwarf a million suns. Now, take a moment to look up at the night sky. What do you see? A vast, seemingly endless expanse, mostly dark, dotted with distant stars and galaxies. Between these celestial islands, there stretches an immense, profound emptiness. This cosmic void appears overwhelmingly cold, its darkness punctuated only by the sparse pinpricks of light from distant suns. Indeed, instruments confirm this perception. The average temperature of the interstellar medium, far from any star, plummets to just a few Kelvin above absolute zero, a frigid 270 degrees Celsius. This stark contrast presents a profound cosmic paradox. If our universe began as an unimaginably hot, dense fireball, a state of universal incandescence, where is the lingering heat? Where is the pervasive glow that should surely remain as an echo of such a cataclysmic birth? The laws of physics dictate that energy cannot simply vanish, it transforms. So if the universe was once a fiery furnace, what became of its radiant heat? This question hung over cosmology for decades, a fundamental puzzle at the heart of understanding our origins. If you light a fire, it eventually dies down, but its warmth persists for a time, radiating outwards into the surroundings. If you turn off an oven, it doesn't instantly become cold. It continues to emit heat, a residual warmth that fills the kitchen. The universe, in a sense, is like an impossibly vast cooling oven. If it was once searingly hot, there must be some residual warmth, some relic radiation, spread across all of space, even if greatly diminished and cooled by billions of years of expansion. The challenge was to find this faint, pervasive glow, to detect this ancient warmth amidst the vast cold and darkness. The search for this cosmic afterglow was, in many ways, a search for the universe's earliest autobiography, a direct message from a time when it was barely a fraction of its current age. For the first few 100,000 years after the Big Bang, the universe was too hot for stable atoms to form. It existed as a dense, turbulent plasma, a soup of free-floating protons, electrons, and photons. Imagine trying to see through an impossibly thick fog. Light particles, or photons, were constantly bumping into free electrons, unable to travel far without being scattered. This made the early universe effectively opaque, a brilliant, blinding haze that prevented any light from traversing significant distances. There were no stars or galaxies yet, only this uniform, superheated glow, an all-encompassing brightness that filled every corner of the nascent cosmos. Then, a critical transformation occurred. As the universe expanded, it also cooled. Around 380,000 years after the Big Bang, the temperature dropped sufficiently to approximately 3,000 Kelvin, about 2,127 degrees Celsius, for electrons to combine with atomic nuclei primarily hydrogen and helium, to form the first stable neutral atoms. This event, known as recombination or decoupling, marked a pivotal moment in cosmic history. Suddenly, the universe became transparent. With electrons now bound within atoms, photons could travel freely without constantly colliding and scattering. It was as if a dense fog had suddenly lifted, allowing light to stream out across the cosmos for the very first time. These photons, released from the primordial plasma, began an uninterrupted journey that has lasted for 13.8 billion years, traveling across an ever-expanding universe to reach us today. This ancient light, now incredibly stretched and cooled by the universe's expansion, is what we call the cosmic microwave background, or CMB. It is the oldest light we can detect, a pervasive, faint glow that permeates all of space. When these photons were first released, they were energetic, corresponding to visible and infrared light. However, as the universe expanded over billions of years, the very fabric of space stretched these light waves, increasing their wavelength and decreasing their energy. This phenomenon, known as cosmological redshift, means that what was once brilliant visible light has been stretched down into the microwave portion of the electromagnetic spectrum, far beyond what human eyes can perceive. It is the ultimate fossil radiation, a universal hum that washes over us from every direction, carrying information about the universe when it was just a tiny fraction of its current age. The CMB is not just a uniform static. It is a profound message, an echo from the dawn of time itself. It tells a story of an infant universe, a story etched in the subtle variations within its glow. While remarkably uniform across the sky, there are incredibly tiny temperature differences, often just a few parts in 100,000, across this background radiation. These minuscule fluctuations are not random noise. They are the imprints of slight density variations in the primordial plasma, the very seeds from which all cosmic structure, stars, galaxies, and vast galaxy clusters would eventually grow under the relentless pull of gravity. Imagine the universe as a perfectly smooth, featureless canvas, and these tiny fluctuations as the first, almost imperceptible brushstrokes, destined to become the magnificent cosmic tapestry we observe today. This faint microwave glow is a direct, tangible link to the Big Bang, serving as our most compelling piece of evidence for the universe's hot, dense origin and subsequent expansion. It surrounds us completely, bathing Earth, our solar system, and every galaxy in a steady, cold bath of microwave radiation. If our eyes could perceive microwaves, the entire sky would appear to glow with a uniform, albeit dim, orange-red hue, like looking into a warm, gently pulsing light source that encompasses everything. It is a constant reminder of our cosmic lineage, a whisper from an infant universe, traveling across unimaginable distances and timescales to reach us, offering invaluable insights into the fundamental nature of reality and our place within it. It is the universe's earliest baby picture, an image frozen in time just after it shed its opaque veil, revealing the blueprints for everything that was to come. Imagine, if you will, the universe not as the vast dark expanse we perceive today, but as an unimaginably dense, superheated fog. This was the state of the cosmos for its earliest moments, a turbulent, brilliant cauldron where the very fabric of existence was fundamentally different. We call this initial state a plasma, a term typically used to describe the fourth state of matter, distinct from solids, liquids, and gases. In a plasma, atoms are so intensely heated that their electrons are stripped away from their nuclei. Instead of neatly bound atoms, The universe was a chaotic, ionized soup of free-floating protons and electrons, along with an immense number of energetic photons, the fundamental particles of light. Picture this primeval soup. It was not merely hot, it was incandescently hot, with temperatures soaring into the billions of Kelvin in the first fractions of a second after the Big Bang, eventually cooling to several thousands of Kelvin by the time a few 100,000 years had passed. At these extreme temperatures, the forces holding electrons to atomic nuclei simply could not compete with the sheer energy of the environment. Every time an electron might briefly attempt to bond with a proton, an energetic photon would instantly collide with it, ripping it free again. This meant that light, in the form of these photons, was constantly interacting with the free electrons and protons. It was like being trapped inside an infinitely dense, shimmering cloud, where every particle of light could only travel an infinitesimal distance before scattering off another charged particle. This constant interaction had a profound consequence. The early universe was utterly opaque. Light could not travel freely for any significant distance. Imagine trying to see through the heart of a star, or a fog so thick it blots out the sun even at arm's length. That was the cosmic reality. Photons were effectively thermalized, meaning they were in a state of thermodynamic equilibrium with the matter, constantly exchanging energy and momentum. They were absorbed, re-emitted, and scattered in every conceivable direction, unable to escape the dense, charged medium. This period of cosmic opacity lasted for an astonishing 380,000 years after the Big Bang, a duration that, while brief in the grand sweep of cosmic history, was a transformative age for the universe. During this time, the universe was expanding rapidly, and as it expanded, it cooled. This cooling was the crucial prerequisite for the universe to transition from its opaque, plasma state to the transparent cosmos we inhabit today. The pivotal event that marked this transition is known as the epoch of recombination, sometimes also referred to as decoupling. The term recombination is a slight misnomer, as it implies electrons were combining with nuclei again. In reality, this was the first time electrons were able to stably bind with nuclei to form neutral atoms. Before this epoch, the universe was simply too hot. But as the universe continued to expand, its temperature steadily dropped. From billions of Kelvin, it cooled down to several 100 million, then tens of thousands, and eventually, around 380,000 years after the Big Bang, the average temperature of the universe reached approximately 3,000 Kelvin. To put this in perspective, 3,000 Kelvin is roughly the temperature of the surface of a cool red star, or the filament in an incandescent light bulb. At this critical temperature, the average energy of the photons in the universe finally fell below the ionization energy of hydrogen and helium. Hydrogen, being the simplest atom with just one proton and one electron, requires 13.6 electron volts, eV, of energy to ionize it, meaning to rip its electron away. When the universe was hotter, most photons possessed energies greater than 13.6 eV, making it impossible for neutral hydrogen atoms to persist for long. But once the temperature dipped below 3,000 Kelvin, the photons, on average, no longer carried enough energy to keep the electrons unbound. It was like a cosmic game of musical chairs, where suddenly there were enough chairs, protons and helium nuclei for the players, electrons, to finally settle down. The process unfolded over tens of thousands of years, but it reached its peak around the 380,000 year mark. Electrons, now less frequently bombarded by high-energy photons, could finally recombine with protons to form neutral hydrogen atoms and with helium nuclei to form neutral helium atoms. This seemingly simple change had monumental implications. Once electrons were bound within neutral atoms, they presented a far smaller target for photons. Free electrons are highly effective at scattering light, but neutral atoms are largely transparent to most wavelengths of light. Imagine trying to throw a ball through a room full of ping-pong balls bouncing freely versus a room where all the ping-pong balls are glued to the floor. The second scenario offers a much clearer path. This transformation from an ionized plasma to a universe filled predominantly with neutral atoms fundamentally altered the cosmic landscape. It was the moment of decoupling, when matter and radiation effectively went their separate ways. The photons, which had been trapped in the cosmic fog for hundreds of millennia, were suddenly free. They could now travel enormous distances without scattering or being absorbed. This was the moment the universe became transparent. It was as if a thick, impenetrable veil was lifted, allowing light to stream unimpeded across the nascent cosmos. These newly liberated photons are the very light we detect today as the cosmic microwave background. They embarked on an epic journey, traveling across the expanding universe for 13.8 billion years to reach our telescopes. When they were first released, these photons had the energy corresponding to a temperature of about 3000 Kelvin, meaning they would have appeared as a yellowish-orange glow, similar to the light from a very hot lamp. However, the universe has been continuously expanding since that time. As space itself expanded, the wavelengths of these photons were stretched, a phenomenon known as cosmological redshift. This stretching caused their energy to decrease, shifting their color from visible light through infrared and eventually into the microwave portion of the electromagnetic spectrum. Today, these ancient photons, having cooled significantly due to the universe's expansion, correspond to a mere 2.725 Kelvin above absolute zero. This is why we observe them as faint microwaves, rather than a brilliant visible glow. The surface of last scattering is a conceptual boundary, not a physical one, representing the point in time and space where these photons last interacted with matter before streaming freely. It's like looking at the surface of a cloud. You are not seeing a solid object, but rather the point where the light last scattered off the water droplets before reaching your eyes. In the case of the CMB, we are looking back to the surface of the opaque early universe, witnessing the universe's oldest baby picture, imprinted with the conditions of that pivotal moment of transparency. This faint afterglow, this echo from the Big Bang, carries with it an unparalleled wealth of information about the universe's infancy, waiting for us to decipher its ancient message. The universe, in its earliest infancy, was a superheated, opaque fog, a plasma dense enough to trap light within its fiery embrace. Yet, as it expanded and cooled for approximately 380,000 years, a profound transformation occurred, the formation of neutral atoms, rendering the cosmos transparent. This pivotal moment released a flood of photons, a primordial glow that has been traveling across the vast expanse of space ever since, stretched and cooled by the universe's ceaseless expansion into what we now detect as the cosmic microwave background, or CMB. This ancient light is a direct snapshot of the universe at a mere fraction of its current age, a silent testament to its origins. Decades before this ancient light was actually detected, its existence was theoretically predicted, though these groundbreaking insights were initially overlooked by the wider scientific community. In the late 1940s, a visionary group of physicists, led by George Gamow, and including his brilliant colleagues Ralph Alpher and Robert Herman, were delving into the intricate processes of the early universe. Their work centered on Big Bang nucleosynthesis, the theory explaining how the lightest elements, hydrogen, helium, and trace amounts of lithium, were forged in the immediate aftermath of the Big Bang. As they meticulously modeled these nuclear reactions, a crucial implication emerged from their calculations. If the universe had indeed begun in a hot, dense state, there must be a residual heat, a faint afterglow permeating all of space, a kind of fossil radiation left over from that fiery epoch. Alpha and Herman, building on Gamow's foundational ideas, went further, even predicting the approximate temperature of this cosmic background radiation. Their initial estimates placed it around 5 Kelvin, or 268 degrees Celsius, a temperature just above absolute zero. This prediction, published in 1948, was a remarkable intellectual leap, suggesting that the universe should be bathed in a uniform, low-energy radiation detectable as microwaves. Imagine trying to hear a whisper from the very dawn of time, a sound so faint it blends into the background hum of existence. That's what Gamow, Alpha, and Herman had theoretically pinpointed, a specific frequency of light that had been stretched from visible wavelengths into the microwave spectrum by billions of years of cosmic expansion. Despite the profound implications of their work, it remained largely unappreciated and, for a time, forgotten. The scientific landscape of the mid-20th century was bustling with other exciting discoveries and theoretical debates. There was no readily available technology capable of detecting such incredibly faint microwave signals, and the focus of many physicists was elsewhere, perhaps on particle physics or alternative cosmological models like the steady-state theory, which posited an eternally unchanging universe without a fiery beginning. Consequently, the groundbreaking prediction of this cosmic afterglow lay dormant, a theoretical jewel awaiting its observational confirmation. Fast forward to the early 1960s, specifically to the sprawling, technologically advanced grounds of Bell Telephone Laboratories in Holmdel, New Jersey. This was a hub of innovation, a place where some of the most significant advancements in communication technology were being forged. Here, two radio astronomers, Arno Penzias and Robert Wilson, found themselves engaged in a project seemingly unrelated to the grand questions of cosmology. Their task was to test a new, highly sensitive horn antenna, a massive, gleaming metallic structure designed for cutting-edge satellite communication experiments, particularly with NASA's Echo and Telstar satellites. The antenna was a marvel of engineering for its time, built to capture incredibly weak radio signals bounced off orbital reflectors or transmitted from distant satellites. Penzias and Wilson were meticulous scientists, striving for absolute precision. Their goal was to measure the faint radio signals from space with unprecedented accuracy, which meant eliminating every possible source of interference or noise. They aimed to calibrate the antenna to detect signals as close to absolute zero as possible, effectively tuning out all unwanted background radiation. However, as they meticulously worked through their measurements, a persistent, annoying hiss or static refused to disappear. It was a faint, uniform signal, equivalent to about 3.5 Kelvin of extra temperature, emanating from every direction they pointed their highly directional antenna. This was a deeply puzzling anomaly, a stubborn whisper in their receivers that defied all conventional explanations. Their initial efforts to identify the source of this pervasive noise were exhaustive, bordering on the obsessive. Imagine the frustration. Two brilliant minds, equipped with state-of-the-art technology, meticulously eliminating every conceivable terrestrial and instrumental source of interference, only to find the signal stubbornly persisting. They checked all the electronic components, scrutinizing connections, cables, and amplifiers for any malfunction. They even cooled their sensitive detector with liquid helium to minimize its own thermal noise. They repeatedly aimed the antenna towards various parts of the sky, hoping to localize the source, perhaps attributing it to military radar, distant radio broadcasts from New York City, or even solar radiation. But the signal remained isotropic, meaning it was uniformly present regardless of where the antenna was pointed, and it was constant, day and night, season after season. Their troubleshooting extended beyond the purely electronic. They considered atmospheric interference, perhaps rain, humidity, or other weather phenomena were causing the noise. But the signal persisted even on clear, dry days. Then, a more mundane, yet memorable theory emerged. Pigeons. A pair of pigeons had taken up residence inside the large, flared mouth of their horn antenna, leaving behind a layer of what Penzias famously described as white dielectric material, or simply pigeon droppings. Convinced that these avian tenants and their accumulated waste might be scattering radio waves or generating thermal noise, Penzias and Wilson meticulously cleaned the entire interior of the antenna, even removing the pigeons themselves. They hosed down the structure, scrubbing away every trace of the bird's presence. But even after this rather unpleasant and thorough cleansing, the mysterious 3.5 Kelvin hiss remained, unwavering and omnipresent. The universe, it seemed, was still whispering. Their growing bewilderment was palpable. They had exhausted all their conventional explanations for the persistent noise. It wasn't terrestrial. It wasn't instrumental. It wasn't even pigeons. This left them in a scientific quandary, a state of profound uncertainty that often precedes a major breakthrough. They were observing something fundamental, something that appeared to be coming from beyond Earth, beyond the solar system, and indeed, beyond our own galaxy. The signal was too uniform, too constant, and too pervasive to be anything localized. They were, in essence, listening to the universe itself, but they didn't yet know it. The crucial connection between their inexplicable static and the universe's oldest light was made through a serendipitous chain of events. Penzias happened to make a phone call to Bernard Berg, an astronomer at MIT, to discuss some unrelated radio astronomy data. During their conversation, Penzias mentioned the persistent, unexplained noise plaguing their horn antenna. Berg, recognizing the significance of such an isotropic signal, recalled hearing about a group at Princeton University who were actively searching for precisely such a cosmic background radiation. This Princeton group was led by the distinguished physicist Robert Dicker, who, independently, had rediscovered the theoretical arguments for a cosmic background radiation. Dicker and his colleagues, including Jim Peebles, P.G. Roll, and David Wilkinson, were actually in the process of building their own radiometer designed specifically to detect this very signal, inspired by Gamo's earlier overlooked work. When Penzias called Dicker, describing the uniform 3.5 Kelvin excess noise they couldn't eliminate, the pieces of the cosmic puzzle clicked into place. Dicker reportedly remarked, "Boys, we've been scooped." The inexplicable static that Penzias and Wilson had so diligently tried to remove was, in fact, the very signal Dicker's team was attempting to detect. The realization was profound. Penzias and Wilson had, by accident, stumbled upon the most direct observational evidence for the Big Bang. Their persistent static was not interference, but the faint, ancient echo of the universe's earliest moments. The cosmic microwave background radiation predicted decades earlier by Gamow, Alpha, and Herman. It was the cooled and stretched leftover radiation from the epoch of recombination, when the universe became transparent. This accidental discovery marked a pivotal moment in cosmology, providing incredibly strong support for the Big Bang model over its main competitor, the steady-state theory, which struggled to account for such a ubiquitous background radiation. In 1965, two landmark papers were published side by side in the Astrophysical Journal. The first, authored by Penzias and Wilson, precisely described their observations of a measurement of excess antenna temperature at 4080 Ze/McKe-s. The second, by Dicker, Peebles, Roll, and Wilkinson, provided the cosmological interpretation, explaining that the observed excess noise was consistent with the cosmic blackbody radiation predicted by the Big Bang model. This simultaneous publication perfectly encapsulated the scientific process: meticulous observation meeting profound theoretical explanation. The impact of this discovery was immediate and transformative. It provided concrete, observational proof that the universe had indeed begun in a hot, dense state and had been expanding and cooling ever since. The 3.5 Kelvin signal measured by Penzias and Wilson, later refined to 2.725 Kelvin, was the perfect blackbody spectrum, a hallmark of thermal radiation from a uniform, hot source that has expanded and cooled. This wasn't just another scientific finding. It was a window into the universe's infancy, a direct message from the dawn of time. For their groundbreaking, albeit accidental discovery, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics in 1978. Their meticulous efforts to eliminate every possible source of noise, even the pigeons, ultimately led them to hear the universe's oldest whisper. Their discovery not only confirmed a fundamental prediction of the Big Bang, but also opened up an entirely new field of cosmological research, allowing humanity to look back in time and study the universe as it was nearly 13.8 billion years ago. The persistent static, once a source of immense frustration, became the clearest sound of our cosmic origins, a message carried across billions of light years, revealing the universe's earliest childhood. The cosmic microwave background, as initially observed by Arno Penzias and Robert Wilson, presented itself as an astonishingly uniform glow, a pervasive hum of radiation emanating from every direction in space. This uniformity, a temperature of approximately 2.7 Kelvin, was in itself a profound confirmation of the Big Bang model. It suggested that the early universe, at the epoch of decoupling, was remarkably homogeneous, an almost perfectly smooth cosmic broth. Imagine a vast, perfectly still ocean, its surface unmarred by even the slightest ripple. That was the initial impression of the CMB. This grand uniformity was precisely what physicists expected from a universe that began everywhere simultaneously, in a hot, dense state. However, this very uniformity also presented a deep, unsettling paradox. If the universe truly began as an utterly smooth, featureless expanse of hot gas and radiation, then how did anything ever form? Gravity, the architect of cosmic structure, requires initial differences, however subtle, to begin its work. A perfectly smooth distribution of matter would remain perfectly smooth forever, unable to coalesce into stars, galaxies, or the intricate cosmic web we observe today. Without some initial gravitational lumps, the universe would be a uniform, diffuse fog of hydrogen and helium, eternally sterile and dark. This fundamental question haunted cosmologists. Where did the seeds of cosmic structure come from? The answer lay hidden within that seemingly uniform glow, far beyond the detection capabilities of Penzias and Wilson's groundbreaking antenna. Scientists theorized that there must be minuscule variations in the CMB's temperature, tiny anisotropies, as they are called, meaning not perfectly uniform or isotropic. These anisotropies would be the faint imprints of equally tiny density fluctuations that existed in the universe just 380,000 years after the Big Bang. Picture that perfectly still ocean again, but now imagine that if you looked incredibly closely, with instruments of extreme precision, you might discern the most delicate, almost imperceptible undulations, waves perhaps only a few molecules high, hinting at deeper currents or distant forces. These cosmic undulations, these subtle deviations from perfect uniformity, were the crucial missing piece of the puzzle. To detect these incredibly subtle variations, humanity needed to look beyond Earth's atmosphere, which absorbs and distorts much of the microwave radiation. The solution came in the form of a dedicated space mission, the Cosmic Background Explorer, or COBE satellite. Conceived in the late 1970s and meticulously designed and built over a decade, COBE represented a monumental leap in our ability to probe the universe's earliest moments. Its mission was ambitious: to precisely measure the diffuse infrared and microwave radiation from the early universe, effectively mapping the afterglow of the Big Bang with unprecedented accuracy. Finally, after years of planning and construction, COBE was launched on November 18, 1989, from Vandenberg Air Force Base aboard a Delta rocket. It was a moment of immense anticipation for the scientific community. The satellite, resembling a large squat cylinder adorned with solar panels and shielded by a sunshade, was placed into a polar orbit approximately 900 kilometers above Earth. From this vantage point, it could scan the entire sky every 6 months, far removed from terrestrial interference and atmospheric noise. Inside COBE were 3 main instruments, each designed to tackle a specific aspect of the cosmic background radiation. The Diffuse Infrared Background Experiment, DIRBE, aimed to search for the infrared background light from the first stars and galaxies. The Far Infrared Absolute Spectrophotometer, FIRAS, was tasked with precisely measuring the spectrum of the CMB. And most critically for the search for structure, the Differential Microwave Radiometer, DMR, was designed to detect those elusive, tiny temperature differences across the sky. The first major triumph of the COBE mission came from the FIRAS instrument, led by John C. Mather. Its task was to measure the CMB spectrum, essentially charting the intensity of the radiation across different microwave frequencies. The Big Bang theory predicted that this radiation should have a perfect blackbody spectrum, the characteristic emission of an ideal thermal radiator. Imagine heating a piece of metal. As it gets hotter, it glows, first dull red, then orange, yellow, and eventually white hot, emitting a continuous spectrum of light. A blackbody curve is a very specific, smooth, bell-shaped curve that describes this emission, and its peak depends directly on the object's temperature. If the CMB truly was the leftover heat from a hot Big Bang, its spectrum had to match this theoretical blackbody curve. The results from FIRAS were nothing short of spectacular. Within 9 minutes of operation, FIRAS collected enough data to confirm the prediction. The CMB spectrum was not merely close. To a blackbody, it was the most perfect blackbody spectrum ever measured in nature. It matched the theoretical curve with astonishing precision, with deviations no larger than 1 part in 10,000, confirming a temperature of 2.725 Kelvin. This was a monumental validation of the Big Bang model, a definitive piece of evidence that the universe had indeed begun in a hot, dense state. It was like hearing a perfect, sustained, pure tone from the universe, confirming its origin. John C. Mather would later share the Nobel Prize in Physics for this groundbreaking work. Yet, the ultimate prize, the key to unlocking the universe's structural history, lay with the DMR instrument, spearheaded by George F. Smoot. This instrument was designed to search for those tiny temperature fluctuations, the anisotropies, against the overwhelming uniformity of the 2.725 Kelvin background. This was an incredibly delicate measurement. The anticipated variations were on the order of microkelvins, millionths of a degree. To put this into perspective, imagine trying to detect a temperature difference equivalent to heating one side of a swimming pool by less than 1,000th of a degree Celsius, while the entire pool is already at a uniform, chilly temperature. The DMR achieved this by rapidly switching its observation point between different parts of the sky, comparing the microwave intensity from one direction to another, and meticulously subtracting out any local interference from our galaxy or Earth. For nearly 2 years, COBE diligently mapped the sky. The scientific team, led by Smoot, pored over the data, meticulously cleaning it of foreground emissions from our own Milky Way galaxy, which can be much brighter than the faint CMB signal. It was a painstaking process, filtering out everything that wasn't the primordial signal. And then, in April 1992, the announcement came that sent ripples through the scientific world. The COBE DMR had indeed detected the cosmic anisotropies. The maps revealed tiny hot and cold spots in the CMB, temperature fluctuations of approximately 1 part in 100,000, or about 30 microkelvins. These were not random noise. They were structured patterns, like faint swirling currents on the surface of that primordial ocean. This discovery was monumental. It was, as George Smoot famously described it, like looking at the face of God. For the first time, humanity had a direct image of the universe when it was just 380,000 years old, an image imprinted with the seeds of everything we see today. These tiny temperature differences corresponded to equally tiny density fluctuations in the early plasma. Where the temperature was slightly higher, the density was fractionally lower, and where it was slightly colder, the density was fractionally higher. Imagine a vast, almost perfectly uniform cloud of gas, but with some regions ever so slightly more concentrated, perhaps by a tiny fraction of a percent. These imperceptible variations were the gravitational seeds from which all cosmic structures, stars, galaxies, and gigantic galaxy clusters eventually grew. The process of structure formation is a slow, majestic cosmic dance governed by gravity. In the slightly denser regions of the early universe, gravity exerted a marginally stronger pull. Over the ensuing billions of years, these denser pockets acted as gravitational wells, slowly but inexorably, attracting more and more of the surrounding hydrogen and helium gas. It was an incredibly gradual process. The initial density enhancements, perhaps only 1 part in 100,000, grew over time. As more matter accumulated, gravity strengthened further, accelerating the collapse. These growing lumps eventually became the birthplaces of the first stars, which then grouped together to form the earliest galaxies. Galaxies, in turn, were drawn into larger structures, forming galaxy clusters and superclusters, strung together in a vast filamentary cosmic web, separated by enormous voids. Without these initial minute fluctuations, this intricate cosmic architecture would never have emerged. The universe would have remained a smooth, undifferentiated expanse. The COBE results provided direct observational evidence for the origin of this structure, tying the elegant theory of the Big Bang to the complex reality of the universe we inhabit. It was a profound confirmation of our understanding of cosmic evolution. showing that the seemingly random distribution of galaxies across the sky had its origins in these microscopic quantum fluctuations from the very earliest moments, stretched across the cosmos by the universe's rapid expansion. George F. Smoot, alongside John C. Mather, was awarded the Nobel Prize in Physics in 2006 for their leadership in the COBE mission, a testament to the profound impact of their findings. The COBE data not only confirmed the Big Bang, but also laid the foundation for precision cosmology, allowing scientists to begin to measure the fundamental parameters of the universe with unprecedented accuracy. The faint whispers of the early universe had finally been heard, revealing the blueprint for everything that followed. The cosmic microwave background, or CMB, is far more than just a faint ancient glow. It is a profound message, a cosmic Rosetta Stone etched with the universe's autobiography, revealing fundamental truths about our existence. The subtle patterns and tiny fluctuations within this primordial light are not merely noise. They are the most comprehensive record we possess of the universe's earliest moments, a treasure trove from which scientists can extract precise parameters describing the entire cosmos. Imagine holding a single ancient parchment that, when deciphered, tells the complete story of your lineage, the exact composition of your ancestors, and the very shape of the land they inhabited. That is what the CMB represents for the universe. One of the most remarkable revelations from the CMB is the universe's precise age, 13.8 billion years. How can observing a faint microwave signal tell us this with such accuracy? The answer lies in understanding the universe's expansion. The CMB was emitted about 380,000 years after the Big Bang, when the universe cooled enough to become transparent. Since then, these photons have been traveling across an ever-expanding cosmos. By precisely measuring the properties of the CMB, particularly its temperature variations and the average density of matter and energy, cosmologists can infer the rate at which the universe has been expanding since that moment. This expansion rate, often called the Hubble constant, allows us to effectively rewind the cosmic clock. If we know how fast the universe is expanding now, and how its expansion has changed over time due to the influence of matter and energy, we can calculate precisely when all matter and energy must have been compressed into the incredibly dense state we call the Big Bang. The precision of this age determination has been refined over decades, notably by missions like the Cosmic Background Explorer, COBE, which first confirmed the CMB's blackbody spectrum and detected its anisotropies, and then dramatically improved by the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite. These later missions provided exquisitely detailed maps of the CMB, allowing scientists to pin down cosmological parameters with unprecedented accuracy. The angular scales of the hot and cold spots in the CMB map, for instance, act like cosmic rulers. They are the imprints of sound waves that propagated through the early universe's plasma. The physics of these waves is well understood, so their size at the moment of decoupling can be calculated. By comparing their known intrinsic size to their apparent size on the sky today, and factoring in the expansion of space, scientists can precisely determine the distance these photons have traveled and, consequently, the age of the universe. This journey of photons, stretched and cooled, directly translates into the grand timescale of cosmic evolution. Beyond its age, the CMB also serves as the primary evidence for the universe's surprising composition. When we look out into the cosmos, we see stars, galaxies, and gas clouds, what we call ordinary matter or baryonic matter. However, The CMB tells a different story. The specific patterns in the temperature fluctuations, particularly the relative heights and positions of the acoustic peaks in the CMB power spectrum, act as a cosmic fingerprint, revealing the proportions of different components that make up the universe. Imagine striking a bell. The sound it produces, its pitch and overtones, depends on the material, size, and shape of the bell. Similarly, the sound waves in the early universe's plasma left imprints on the CMB, and the characteristics of these imprints tell us about the ingredients of the universe. For instance, the height of the first acoustic peak on the CMB power spectrum is highly sensitive to the density of ordinary matter. From these measurements, we've learned that ordinary matter, the stuff of stars, planets, and ourselves, constitutes only about 4.9% of the total mass energy density of the universe. This is a remarkably small fraction, suggesting that the vast majority of the cosmos is made of something else entirely. The existence of this missing matter, which interacts gravitationally but does not emit, absorb, or reflect light, had been inferred from galactic rotation curves and galaxy cluster dynamics for decades. However, the CMB provided independent and powerful confirmation of what we now call dark matter. Dark matter, which makes up about 26.8% of the universe, does not interact with light, but its gravitational pull significantly influenced the oscillations in the early universe's plasma. The presence of dark matter affected the gravitational potential wells in which the ordinary matter and photons were oscillating, thereby altering the relative heights of the CMB's acoustic peaks, particularly the second and third ones. While baryonic matter feels the pressure of photons pushing it around, dark matter only feels gravity. This difference in behavior left distinct imprints on the CMB, allowing scientists to precisely measure its abundance. It acts as a kind of invisible scaffolding, providing the extra gravitational glue needed for the initial density fluctuations to grow into the vast cosmic structures we observe today. Perhaps even more enigmatic is dark energy, which accounts for approximately 68.3% of the universe's total mass energy density. Dark energy is a mysterious force responsible for the accelerated expansion of the universe. While its direct influence on the early universe's sound waves was less pronounced than matter, its presence significantly affects the overall geometry of the universe. The CMB provides crucial evidence for dark energy because the apparent angular size of the acoustic peaks on the sky is extremely sensitive to the universe's curvature, which in turn depends on the total energy density, including dark energy. A specific combination of matter, and dark energy is required to make the universe spatially flat, a condition strongly supported by CMB observations. This brings us to another profound revelation from the CMB: the universe's geometry. The CMB confirms that the universe is, on large scales, remarkably flat. What does a flat universe mean? In cosmology, geometry refers to the overall shape of space. Imagine drawing a very large triangle in space, using light rays as its sides. In a flat universe, the angles of that triangle would add up to exactly 180 degrees, just like on a flat piece of paper, Euclidean geometry. In a positively curved universe, like the surface of a sphere, the angles would add up to more than 180 degrees. In a negatively curved universe, like a saddle, they would add up to less. The CMB acts as a cosmic surveyor, allowing us to measure this curvature. The angular size of the hot and cold spots in the CMB map serves as a standard ruler. We know, from the physics of the early universe, the actual physical size of these initial sound waves at the moment the CMB was emitted. By measuring how large these features appear to us on the sky today, we can determine the geometry of the space through which their light has traveled. If the universe were positively curved, these spots would appear magnified, larger than their true angular size. If it were negatively curved, they would appear demagnified, smaller. The incredibly precise measurements from WMAP and Planck, analyzing hundreds of thousands of these spots across the entire sky, show that their apparent angular size is exactly what would be expected in a flat universe. This finding is a cornerstone of modern cosmology, implying that the total density of matter and energy in the universe is precisely at the critical density required to make space flat. This flat geometry has profound implications for the universe's ultimate fate, suggesting it will continue expanding indefinitely, albeit at an accelerating rate due to dark energy. With such profound implications derived from the CMB, it is important to address some common misconceptions. Firstly, despite references to acoustic peaks and sound waves in the early universe, the cosmic microwave background itself is light, not sound. The term acoustic refers to pressure waves propagating through the dense, hot plasma of the early universe, similar to how sound waves travel through air or water. However, once the universe became transparent and photons decoupled from matter, these pressure waves ceased to exist as physical phenomena affecting the light directly. The CMB photons are electromagnetic radiation, traveling through the vacuum of space at the speed of light. Sound, by definition, requires a medium to propagate, and the vast emptiness of space is a near-perfect vacuum. While the patterns in the CMB were caused by these primordial sound waves, the signal we detect today is purely light, albeit light, that has been stretched into the microwave portion of the spectrum. Secondly, the observation of the CMB coming to us uniformly from all directions does not imply that the universe had a single center from which the Big Bang exploded. This is a persistent and fundamental misunderstanding. The Big Bang was not an explosion into pre-existing space from a central point, but rather an expansion of space itself. Every point in the early universe was once hot and dense, and every point can be considered the center of its own observable universe. The CMB photons we detect today originated from all directions because we are observing light from the surface of last scattering, the moment the universe became transparent, which is an imaginary spherical shell surrounding us, roughly 13.8 billion light-years away in every direction. Imagine the surface of an expanding balloon with dots drawn on it. As the balloon expands, every dot moves away from every other dot, and no single dot is at the center of the expansion on the surface. Similarly, the CMB light comes from all directions, because the entire observable universe was once in that hot, dense state, and we are simply looking back in time to that epoch in every direction we gaze. The CMB is thus more than just an ancient artifact. It is an active, living dataset that continues to inform and challenge our understanding of the cosmos. Its patterns, once painstakingly mapped, have provided a cosmological standard model, a framework that describes the universe's age, expansion, and composition with astounding precision. It has transformed cosmology from a largely theoretical field into a data-driven science, allowing us to probe the very fabric of space-time and the mysterious forces that govern our universe. Even after decades of intense scrutiny, the cosmic microwave background, or CMB, continues to be a vibrant frontier of cosmological research. This faint, ancient glow, a relic from the universe's earliest moments, still holds secrets, challenging scientists to push the boundaries of observation and theory. While its temperature fluctuations have revealed profound truths about cosmic structure and composition, the next great quest involves deciphering an even more subtle message encoded within its light, its polarization. To understand this next frontier, imagine light not just as a wave, but as a wave that vibrates in a specific direction. When light reflects off a surface or passes through certain materials, its vibrations can become aligned or polarized. This is similar to how polarized sunglasses work, reducing glare by filtering out light waves vibrating in particular orientations. The light of the CMB, having last interacted with free electrons when the universe was just 380,000 years old, also carries a faint imprint of polarization, a subtle alignment in the way its electromagnetic waves vibrate. Scientists categorize CMB polarization into two primary types, E modes and B modes. E modes represent a pattern of polarization that is symmetric, much like the electric field lines emanating from an electric charge. These E modes are primarily generated by the slight density fluctuations that existed in the early universe, those very seeds of structure we discussed earlier, and they have been robustly detected and mapped by missions like WMAP and Planck. They tell us about the normal, prosaic evolution of the cosmos. However, the true prize, the elusive target of current and future experiments, is the detection of B modes. Unlike E modes, B modes exhibit a swirling, asymmetric pattern, reminiscent of magnetic field lines. This distinctive pattern is incredibly difficult to detect, as it is far fainter than the E mode signal and easily obscured by other sources. But if primordial B modes are definitively found, they would be direct evidence of a phenomenon far more profound than density fluctuations. They would be the smoking gun for gravitational waves from the universe's inflationary epoch. Let's take a moment to consider this inflationary epoch, a concept that stretches our imagination to the very edge of comprehension. The Big Bang Theory describes a universe that began incredibly hot and dense, rapidly expanding from that initial state. But for the theory to perfectly explain the universe's observed uniformity across vast scales, its flatness, and the origin of those initial density fluctuations, many cosmologists propose an additional, even earlier period of hyper-rapid expansion, known as inflation. This epoch is theorized to have occurred in the first tiny fraction of a second after the Big Bang, perhaps from 10 nodards, 36 seconds, to 10 nodards, 32 seconds. During this fleeting moment, the universe didn't just expand, it grew exponentially, inflating by a factor of at least 10 upon 26, possibly much more, in an unimaginably short span of time. Such an extreme and rapid expansion would have had dramatic consequences. It would have stretched microscopic quantum fluctuations in space-time itself to macroscopic cosmic scales. These stretched fluctuations would manifest as ripples in space-time, known as primordial gravitational waves. Imagine the fabric of space-time, not as a static backdrop, but as a dynamic, elastic medium. Inflation would have violently shaken this fabric, sending out powerful waves that propagated throughout the nascent universe. When these gravitational waves passed through the hot plasma that would later form the CMB, they would have distorted the local space-time, subtly influencing the paths of photons and the distribution of free electrons. This interaction, a fleeting gravitational handshake, would leave a unique, swirling B-mode imprint on the CMB's polarization pattern. Detecting these B-modes is a monumental challenge. The signal is predicted to be incredibly faint, perhaps just 1/10 millionth the strength of the temperature fluctuations. Furthermore, it is easily contaminated by foreground emissions from our own Milky Way galaxy, such as polarized light from spinning dust grains or energetic electrons spiraling in magnetic fields. Distinguishing the truly primordial B modes from these galactic noise sources requires instruments of exquisite sensitivity and sophisticated analysis techniques. Despite these difficulties, the scientific community is making tremendous strides. Ground-based telescopes, operating in some of the driest and highest places on Earth, are leading the charge. Consider the Atacama Cosmology Telescope, or ACT, nestled high in the Atacama Desert in Chile. This remote, arid location, with altitudes reaching 5,200 meters, 17,000 feet, offers an exceptionally clear and stable atmosphere, crucial for observing the faint microwave signals from space. Water vapor in the atmosphere absorbs microwaves, so a dry environment is paramount. ACT, with its 6-meter, 20-foot primary mirror, meticulously maps the CMB's temperature and polarization across vast swaths of the southern sky. Its observations have already yielded incredibly precise measurements of the CMB's E-mode polarization and have helped to refine our understanding of the universe's expansion rate and its composition. Similarly, the South Pole Telescope, or SPT, located at the geographic South Pole, capitalizes on the unique atmospheric conditions there. The extremely cold, dry, and stable air above the pole provides an unparalleled environment for microwave astronomy. Instruments like SPT and the BICEP Keck array, also located at the South Pole, are specifically designed to search for the elusive B-mode polarization. The BICEP Keck collaboration, for instance, operates a series of small, dedicated telescopes that scan a patch of the sky, meticulously looking for that swirling signature. While an initial announcement of B-mode detection in 2014 by BICEP 2 created immense excitement, subsequent analysis, incorporating data from the Planck satellite, revealed that much of the signal was likely due to polarized dust within our galaxy. This setback underscored the immense difficulty and the need for even more precise measurements and robust foreground removal techniques. This drive for precision is culminating in the planning and construction of the CMB-S4 experiment, a truly ambitious undertaking. This next-generation ground-based observatory will comprise thousands of detectors spread across multiple telescopes, situated in both the Atacama Desert in Chile and at the South Pole. Imagine arrays of hundreds of thousands of superconducting detectors, each cooled to just a fraction of a degree above absolute zero, working in concert to create the most detailed maps of the CMB ever conceived. CMB-S4 aims not only for a definitive detection of primordial B modes, but also to push the boundaries of cosmology in several other directions. With its unprecedented sensitivity, CMB-S4 is expected to provide incredibly precise measurements of the universe's fundamental parameters. This includes refining the age of the universe, improving our knowledge of the Hubble constant, the rate at which the universe is expanding today, and pinning down the exact proportions of ordinary matter, dark matter, and dark energy with even greater certainty. Furthermore, it will allow for a more precise determination of the mass of neutrinos, those elusive subatomic particles that interact only weakly with other matter, and offer new avenues for searching for signatures of other exotic particles or forces that might exist beyond our current standard model of particle physics. The cosmic microwave background remains our most direct window into the earliest moments of existence. It is the universe's baby picture, offering us a glimpse of what the cosmos looked like before stars and galaxies were born, when it was merely a uniform hot fog. from its accidental discovery as a persistent hiss in a radio antenna, to its meticulous mapping by satellites like COBE, WMAP, and Planck. The CMB has transformed our understanding of cosmic origins, confirming the Big Bang and shaping our modern cosmological model. It has revealed the universe's age, its composition, and its flat geometry. Now, as we stand on the cusp of potentially detecting primordial B modes, the CMB promises to unveil even deeper secrets. If gravitational waves from inflation are definitively confirmed, it would provide a monumental validation of the inflationary paradigm, offering a glimpse into physics at energy scales far beyond anything we can replicate on Earth, and shedding light on the very nature of spacetime and quantum gravity. This quest is not merely about confirming a theory. It is about extending humanity's reach back to the first sliver of a second after creation, understanding the forces that shaped everything we see. The echoes of the Big Bang, preserved in the faint microwave glow surrounding us, continue to whisper profound truths across billions of light years. They remind us that the universe is a dynamic, evolving entity, full of hidden messages waiting to be deciphered. Our relentless pursuit of these ancient signals reflects a fundamental human curiosity, a drive to understand our cosmic roots, to piece together the grand narrative of existence. Each new observation, each refined measurement, brings us closer to comprehending the universe's autobiography, written in the very fabric of space-time, and etched into the light that began its journey almost 13.8 billion years ago. The story of the universe's earliest childhood is still being told, and the CMB is its most eloquent narrator, a timeless beacon guiding our intellectual journey through the cosmos.